All right, so we're going to go over this section, and it has quite a bit of important information that's going to help us as we go forward. Some of it we've already learned a little bit about with our Gizmo Lab, and some of it we haven't gone over yet. We've talked a little bit about some of it. So a couple terms, electric current, that's important to note. So it's a rate, so how fast those charges pass a given point. It has a higher current, there are more charges passing through each second. So it's an important thing to measure. You don't want to have too much current passing through, and that can cause some issues, and we'll talk about that. But first, let's talk about the two types of current, and these will come up again. So AC means alternating current. So the charges shift from flowing in one direction to the reverse. So if you think about the outlets in your home, those are great examples of alternating current. The electricity, the charges flow from one direction and then reverse. DC is direct current, so it flows only in one direction. So a great example of DC or direct current would be batteries. So they only flow in one direction. So if you think of it like a one-way on the street, the charges can only flow in one direction. Where alternating current, they can go back and forth. So that's just a visual to help us remember that. So voltage is something you've probably heard of before. For example, we measure the voltage of batteries for when we're using them in appliances and such. So it is what we say the potential difference between 2 points. So we measure it in what we call volts. So for example, here's some batteries, which we watched a video on. So these batteries are made with various voltages, so we can use them in different devices. For example, this one here is kind of like maybe even a car battery or like a larger like ATV type vehicle. Car batteries might even be a little bit bigger. So this is a 12-volt battery. And then we have other batteries. This is a 6-volt battery that would be used in larger things. And then like the smaller batteries that we use in our house, the A's, the like AA, AAA, C's and D's, those are about 1.5 volts. And then we have what's called a 9-volt battery. That would be like in your smoke detectors if you have ones that put batteries in them. So most appliances are made to run on 120 volts. So if you look at your outlets in your house, most of the outlets in your house are 120 volts if it's a normal outlet. Now, it's important to note that things like ovens, your stove, has a completely different plug with a completely different cord. It's different than a normal one because it needs more voltage. And if you try to draw too much from an outlet, it will flip a switch for the breaker box, which we'll talk about as well. So just to kind of mention as well, this is kind of cool. Some animals can create voltage. So the electric eel can generate 600 volts. So that's pretty amazing. It gives off energy as electricity, where you and I give off energy as heat. So we need to be able to be careful that we don't have too much current flowing through wires. So we have what's called resistance. So you do, to some extent, want to have some resistance in wires, because if you're letting the electricity flow through at just as fast as it wants, that can be very dangerous. So obviously it increases as the temperature increases. So if you have a thin wire, you're going to get more resistance. In other words, those charges can't flow through there because there's less space. Think of it as like when you're on the interstate or the highway and it goes down to one lane, right? It takes longer. Everybody has to take turns. If it's a thick wire, there's less resistance, right? If there's more lanes, more cars can go through and zip by. So if it's a short wire versus a long wire, that's important too. If it's a short wire, it has less resistance than a long. A long would have more resistance. So you can kind of understand the difference. Now they use this analogy of the pipes, right? So think of these as pipes with rocks in them and water's flowing through. So this thicker pipe has less resistance than a thin one, right? And a short one versus a long one, less resistance in the short pipe versus the longer pipe. So it's just kind of visualizing it in a different way. The example I used was the cars. Now, we learned about cells last year in 7th grade, like living cells, but this is a little bit different. When we're talking about electricity, this is a device that produces electric current. So it takes chemical or radiant energy and it turns it to electrical energy. So you guys have probably seen solar cells before, or even like if you use a calculator that's not on your phone, you'll see photocells, which obviously use solar energy or light from the room or outside to power a calculator. Similarly, you have ones that produce electric current that will take maybe chemical energy from a battery, for example. So you have some parts to the cell. You have what's called an electrolyte, and that is what allows charges to flow. So it's a mixture of chemicals. If you've ever seen a battery that's what we say corroded, right? It's broken down. You open it up and there's this powder in it because the chemicals have already reacted and it's too old. Usually in a battery that you would use in your house, it's what we call a dry cell battery. The paste is kind of a powder versus a wet cell, which would be like the ones we use in our car. And those are wet cells because they use a liquid electrolyte. So anyways, there are also electrodes. These are a pair, in pairs usually, and they have conducting materials, for example, copper or zinc. And this is where the charges enter and exit. And then I mentioned the two kinds of cells. You have wet cell batteries, right, that use electrolytes that are liquid. And if you've ever made a lemon clock or seen one, that's a great example. And then dry cell, of course, use a powder, a solid electrolyte. And like I said, those are our smaller batteries that we use in our houses. So this is just an example of how a cell works. So you have your electrodes, right? There's a copper one here and maybe a zinc one here. And what happens is you end up with a chemical reaction. And so there's extra electrons on this electrode. Where do they want to go? They want to go to an area where they can flow, right? And so there's a chemical reaction here in the that causes the electrons to be kind of pulled off one electrode to the other, and this one's made of copper. And so they're connected by a wire, and they're going to go through the wire and move into the electrolyte. So of course cause a current. So this is just a visual of how things are working when you talk about a cell. We have what are also called thermocouples. These convert thermal energy into electrical energy. So heat something up, right, and then it's converted. So they use an example here of a thermocouple. And what happens is this is a Bunsen burner, which we have in our science lab. This is a flame right here. So it's going to heat up this iron and copper wire, right? And there's a meter here that you can see with ice water. And you end up cooling one section, and it's going to convert that energy. So that's just the basics of it. We're not going to spend a lot of time on that. And then I mentioned photocells, right? So you'll see those on solar powered calculators at the top. There'll be maybe 3, 4, 5 of them on a calculator. Nowadays, we don't see them as much, but you've seen solar panels too, right? Out in the sun. You know, some people have them on top of their houses. You'll see them for businesses. Even in places like Arizona, they use them for parking ramps at the top because it's so sunny there. And so this converts light energy, right, into electricity so that we can power our homes, electrical energy for our like appliances and everything with the sun. So that's pretty cool. That's just another example of a type of cell. All right, we'll come back together here.